Okay, let's talk now about regularization. To start talking about regularization, let's check what happens with the weights of our model if we decide to use a polynomial of degree 9. In this table, you can see the values that different models take for the parameters. So for example, in a polynomial of degree 0, we have only one value, which is 0.19 in this case. If you use a polynomial of degree 3, you will have 4 parameters from W0 to W3, and these are the values for each of these parameters. And if you use a polynomial of degree 9, you will have 10 parameters, and here you can see the values that they can take. This is the situation when our model was overfitted, and this is something that we don't want to happen, because when the parameters go crazy like this, they grow very large, to have very large negatives or very large positives, the model is overfitted, and we have a very bad generalization error. So we need to avoid this situation. One way to do that is by increasing the number of data points. Like, for example, if we increase the number of points to be 15, then the model is less overfitted. If we increase it even more and we use 100 points, then the model is very nice, it's very smooth, and it approximates very well the original function, the green curve here. So that is one way to do to avoid overfitting, by increasing the number of points. And this is one of the reasons why we need as much data as possible. So here we can compare two solutions with m equal 9, a polynomial of degree 9. In the left, training with 15 points, and to the right, training with 100 points. Now, there is another way to avoid overfitting, and this is called regularization. In regularization, we need to improve our error function by adding a regularization term. Okay, and in this error function, we see here in the left an error caused by the data. This D comes from data, and this is like the previous error that we saw. Now we need to add this term, which will be the error that is caused by the parameters. Okay, and here we have a lambda constant. This will allow us to play a trade-off between the error caused by the data points and the error caused by the parameters. So if you make lambda to be 0, of course you delete the second term and you care only about the data. And if you increase lambda, then you give it more importance to the error caused by the parameters. So, as I explained before, this ED is the error caused by the data, is the standard square error that we saw previously. Okay, so this expression will be the left side of the general error now, and the right side is defined as the norm of the vector, so the magnitude of the vector of parameters. Okay. Then instead of minimizing the error caused by the data, we will minimize this extended error function, which includes the error with the data and the error caused by large parameters. So if you want to implement a regularized version of a stochastic gradient descent, all you need to do is to add this term in your update rule, where lambda is how important is going to be the size of the parameters, and m is the number of examples that you have. This lambda is another constant that you will need to discover which is the best one for your dataset. And if you want to implement it using normal equations, you just need to add here lambda times the identity matrix. So this is a matrix with only ones in the main diagonal and zeros other way in any other places. So this is the general way to implement regularization. Now you can run experiments with different kinds of norms. So this is the general norm. This Q in this case corresponds to the quadratic regularizer. So in this case you will compute the square root of this norm of the W of the parameter. But you can play with different Qs like 0.5, 1, 2, 4. And these are the shapes that these regularizers take. To understand a bit what is the difference between applying Q2 or Q4, let's see an example of Q2. So these blue contours represent the possible values that the parameters can take. So in this example we are looking at two parameters, W1 and W2. So any position in these contours, blue contours, will represent a specific value of W1 and a specific value of W2. If we were applying this without the regularization is this circle, then the values of the weights could take any value in this plane W1 and W2. They are unbounded. But since we are using regularization, in this case Q equals to this version of regularization, then these contours are attached to the border of this circle. So you can move this circle around, but these circles cannot go away because they are attached to this regularizer. If you use, for example, Q1, then the possibilities of combinations of parameters is attached to this rhombus shaped. Okay. In practical terms, it doesn't make a huge difference actually in most of the cases, but it is important to know what are the consequences in changing the different regularizers. So what are the benefits of regularization? As we have seen, regularization allows complex models to be trained on data sets of limited size without severe overfitting, essentially by limiting the effective model complexity. So when we add this regularization term, what we do is say, okay, we want you to reduce the error to predict the outputs of the inputs values, but also I want you to keep the magnitude of the parameters small. So that's what we are doing when we are applying regularization. We limit the complexity of the model. However, the problem of finding the optimal model complexity is then shifted from one of finding the appropriate number of basis functions to one of determining a suitable value of the regularization coefficient. So the thing is that if you want to do a regularization, then you have one extra parameter that you need to estimate. So that is one of the extra work that you need to do when you apply regularization. And also you can experiment with different values of Q to see if you get a better model. You can estimate a better model.